Today, Roswitha Rissner is coming back to Africa, and she's got a beautiful picture there of a university at Klagenfurt, and it looks absolutely stunning. And we welcome her today. Roswitha is a mathematician at Klagenfurt. She's got very broad research interests, but a very particular interest in developing and using algorithmic methods, in other words, things you can code into a computer, in order to formulate and prove mathematical conjectures. So the title of her talk today is Associated Prime Ideals of Powers of Ideals. Over to you, Roswitha.
Thank you very much for the kind introduction, and thank you very much for the invitation. I really enjoy being here, and I would like to introduce you today to some of my research that I did together with, or I'm doing together with Irina Swanson, a mathematician who is working in the US. So what you see here is actually the campus I'm currently working at. Due to Corona, I'm in lockdown at home. So I'm not there, but I'm not sure whether you can see my pointer. Can you see my pointer?
Yes.
Yes.
So my office is approximately here where the hand is now. So I would be there if not for Corona. Well, that caught all of us. So welcome to my home. And what you see here also is, well, it's a very beautiful picture of my campus during summertime. It's not summer anymore in Austria, so it looks slightly different, but there is a beautiful lake which we use during summer to do our mathematical discussions while swimming. All right, so let me start with my talk today. What I would like to do is, it is my understanding that you're not all algebraists like I am, so I would like to slowly introduce you into the topic by showing you a couple of examples, and then only then give you the necessary definitions. So if you don't understand everything immediately, don't worry, we will get back to that. So let's start with examples. What are associated primes? Most known example is the decomposition of integers. So if you decompose today's date, written as 2020-1104, then at least if I did not make a mistake, it's 2 to the 4th power times 7 times 11 times 19 times 863. And well, it's no big surprise that the prime numbers you see are the associated primes of that particular integer. Only the primes are marked in red and not the 4th power, because we are interested actually in the primes that occur, and we will ignore the multiplicity with which they occur. There's a reason for that, because in more general settings, well, we do not have complete control over that. And a different way of writing the decomposition would be in ideal terms. So if you look at the ideals generated in the ring of integers, as the algebraist now would say, that means you take the integer and look at the set of all multiples of that integers, and we write it in these round parentheses as a shortcut notation. Then this decomposition would also hold as an intersection of the corresponding ideals. Again, the ideals that you see here are generated by prime numbers or powers of prime numbers. So what you get are prime ideals or primary ideals. But as I already promised, you will get to that, back to that later. All you need to take from this slide is, well, a product of integers can also be written as an intersection of ideals. Another example, which I hope you see completely, comes from algebraic geometry. In algebraic geometry, shapes are described as zero sets of polynomials. So the particular shape that you see here, of course, you should think the lines until infinity. This is only a small section of the shape, is described by the polynomial you see on the left-hand side, x cubed minus x times y cubed. So all the points that satisfy this polynomial equation, so are a root of that particular polynomial, lie on the shape, and these are the only ones. So what does that have to do with integer decomposition into primes? Well, you may have noticed the parentheses. Again, this is actually an ideal in a polynomial ring, but ignore that for a second. What you should take from it is that it is again possible to decompose it into two parts, as the shape is consisting of two parts. So what you see here is, I try to mark it in colors. The polynomial x defines you that line, the blue line, and the polynomial x squared minus y cubed defines you this V shape. So the geometric shape that you see that is defined by a polynomial actually consists of two parts, and both of them correspond to somewhat irreducible components. And it happens to be that, again, the two ideals in the intersections are prime components, so they are prime ideals. In polynomial terms, this means they cannot be reduced any further, so they're irreducible, undecomposable. So here again, like before for the integers, we can decompose also a shape into its building blocks, like the prime powers are building blocks of integers. Another example coming from combinatorial commutative algebra is, in my opinion, slightly less intuitive, but maybe if this topic is, if you're closer to this topic, maybe this is exactly the example that you need to understand what associated primes can be. In combinatorial commutative algebra, you can encode graphs into ideal language or in polynomial language. So as an example, I brought this graph that you see here. It has 5 vertices and 3 edges, and each vertex becomes a label. We label them by x1 up to x5 because axes remind us of variables of polynomials. And we translate the graph into an ideal by using monomials in the variables. So the edge x2, x4 becomes the monomial x2 times x4. The edge x1, x4 becomes the corresponding monomial x1 times x4. Third edge, x3, x5, again is expressed as a monomial. And then inside the polynomial ring, you can again generate an ideal by these monomials. We'll get back to that later, not that important right now. And we can decompose it again into building blocks. And the building blocks of this, what is called edge ideal, because it encodes the edges, it decomposes into 4 things. So what are the 4 things? The 4 things, surprisingly, are again, or surprisingly to me maybe, have an interpretation in graph theoretic language. They correspond to minimal vertex cover. So the first component, x3, x4, is a minimal vertex cover of the graph, meaning every other vertex is connected to one of those, and you cannot make it any smaller. If you take one away, then one vertex is not connected anymore. Then instead of x3, x4, you can also take x5, x4, because x3 and x5 are very symmetric in this graph. And if you do not want to take x4, well, then you have to take 3 vertices. x1, x2, x3 is one minimal vertex cover, and again, you can flip x3 and x5 and get another minimal vertex cover. And while if you spend a little bit of time with this graph, then you can easily verify that these are all the minimal vertex covers that you can find. And in ideal language, they are the decomposition into building blocks, into prime building blocks of what is called the edge ideal. So there is a very intrinsic relation between the edges and the minimal vertex covers, even in algebraic terms. You can flip the roles of these two to show you the dual example. You could also interpret the monomials that generate the ideal as the minimal vertex covers. So instead now of multiplying the edge ends with each other, we multiply the vertices of a minimal vertex cover with each other. So you see the same combinations, but now they're multiplied with each other. 1, 2, 3, 4 minimal vertex covers. And now if we algebraically decompose this ideal, what we get are ideals that correspond to the original edges. So if we were to know all minimal vertex covers, we could reconstruct the graph algebraically by looking at these prime building blocks, the edges. Let's check. x1, x4 is there, x2, x4 is there, x3 is 4. x3, x5 is there. So also those are dual to each other, edges and minimal vertex covers, and you can completely understand simple, undirected graphs with no isolated vertices, then it's enough to know all the edges or all the minimal vertex covers to completely understand the whole graph. Of course, you can also see here in this example, computing this decomposition in general is not an easy task. It's actually MP hard because computing minimal vertex covers is a very hard problem. But in theory, well, this information is also encoded in the algebraic point of view. So much for the examples. Let's dive into some definitions. And I also summarized a bunch of facts, which I find to be very important in that context. Let's start with prime and primary ideals. I already mentioned them a little bit. So what we live inside some ring. And for those who do not work with algebra every day, it's completely sufficient for this talk if you imagine that ring to be, for example, all the integers, or if you just imagine a polynomial ring and a bunch of variables over, let's say, the rational numbers. 3 variables x, y, z will occur in the examples. This is something we all know, and while it has an algebraic structure in which we can work in. What is an ideal? Well, let me remind you. An ideal is a substructure of the ring, some part of the ring, which has a certain property. We would like to be able to add and subtract elements inside the ideal without leaving it. So it should be closed on the addition and subtraction. And we would like to multiply arbitrary elements from the ring on this and still stay in the ideal. So it's kind of like in the integers. Well, it's not kind of like, it's actually exactly modeled after the integers. If you look at the set of all multiples of, say, 2, then whenever you add or subtract 2 of them, then they will still be even, so it's divisible by 2, and you can multiply it by any other number. There will still be a 2 in it, so it's still an even number. So ideals in general rings are what the numbers are in the integers, or actually the multiples of the numbers are. For example, all multiples of 24. Even more funny it would have been if I typed here 42, because it's the answer to everything. Maybe I try that in my next talk. A different example, if you now switch to the polynomial ring, you can take an arbitrary polynomial, let's say x squared plus y, and then look at all the polynomial multiples, and you get an ideal of the polynomial ring. So multiples of one element will always do this ideal property thing. What is not an ideal? Well, you cannot take all the odd numbers, for example, because if you add 2 odd numbers, you get an even number and you will leave the set. However, all even numbers form an ideal. So this is a very specific property, and we have to take care that we make sure that it is satisfied. What else do we need? We need prime ideals. Prime ideals are what the prime numbers are for the integers. What we want is whenever we have a product in this ideal, then we want already one of the factors being there. This is like the prime numbers in the integers. Well, you cannot decompose it into 2 parts, both being not 1 or -1. Yeah, so there is no way to further decompose it. And this is the prime. So maybe I try again to point. The ideal property is whenever you put 2 things together, both of them had already, or one of them had already to be there. So it should be a multiple of the prime number, or at least contained in that prime ideal. For polynomials, irreducible polynomials are such a thing. If you cannot decompose it any further, then it generates a prime ideal, but they are not the only ones. Prime ideals can be combinations of several elements. So there's not only multiple of ones, also linear combinations of generators could do the trick. So it gets more complicated in the more general setting. And then let's look at some examples. Well, of course, in the integers, I have already mentioned it, all the prime numbers generate prime ideals. So these are our model primes. We would like to generalize their properties because they help us understand the integers. In the polynomial ring in one variable, all multiples of irreducible polynomials are such a thing. For example, x squared plus 1, if we only allow solutions in the rational numbers. Of course, if we would replace that by the complex numbers, then this would not be irreducible. We would be able to decompose it into linear factors. Now there should be an example which is not a prime ideal. Well, 6 is not a prime ideal of the integers because 2 times 3 definitely is in it, but neither 2 nor 3 are divisible by 6. So this would not be a prime ideal. And again, you can also do this in the polynomial ring, even in more variables. You have an obvious product of 2 things, then it cannot be a prime ideal, the ideal generated by this element, because, well, the factors are already there, but they are not divisible by the product of the 2 factors. Like here, for example, x squared. All right, so the last notion that we definitely need. So we now have ideals, which are the more general numbers in general rings. We have prime ideals, which play the role of prime numbers. And now what we need is, we need some notion of prime power. And here the situation changes completely with respect to the integers. We cannot just simply multiply prime ideals or power of prime ideals and get something that behaves similarly to what prime powers do in the integers. We need a slightly different notion, which keeps the properties that the integers have. And this is called primary ideals. And what primary ideals are, well, I'd like to explain it with the example, all integers that are divisible by 8. So in the integers, it's prime powers. That's the same thing. Yeah, so we don't need to worry. So what is the special property that numbers that are divisible by 8 have? Well, whenever I have a product, a times b, and I know it's divisible by 8, so it is inside this ideal 8z, well, then I know either one of the numbers is already divisible by 8, or both of them are even. So I have 3 times the number 2 in this product. So either they're all in one of the factors, or both of them are divisible by 2. And what that means, in other words, is, well, if they're both not divisible by 8, then some power of them definitely is. Well, in that particular case, we only need to power them up at 3 times, because then we have 2 to the 3 definitely in it, maybe even earlier. So this is the property that we definitely need in a general ring. If we have a product, so up here in the definition, a times b, that is in the ideal, well, then either one of them, so here it's written asymmetrically, either one of them is already in there, like divisible by 8, or the other one can be powered up to something that is divisible by 8, or in this language, in Q. And well, I never mentioned that we are in a commutative setting, so this is definitely the point where I have to admit everything is commutative. AB is equal to BA, so it would also need to hold the other way around for primary. So what you actually have is either A is already in the ideal, or B is already in the ideal, or both of them can be powered up to something that is in the ideal. And with powered up, I mean, they are in some sense a root of something that already lives in the ideal. So we have a root of an element. What other example can I show you? Well, now here, x squared, the ideal generated in the polynomial ring, well, it's not a prime ideal, but it is a primary ideal. When the same argument holds, whenever you have something, a product that is divisible by x squared, then because the polynomial ring allows unique factorization, as well as in the integers, you know that, well, either one of the factors is divisible by x squared, or both already contain a square, an x. And then again, you can power them up and find an x squared in some power of them. So this is what we need for primary. Then again, not surprising, in the integers, so if we do not have a prime power, it's not going to be primary. So for 6, this does not hold. I don't know, for example, now I have to think. Yeah, you just take 2 and 3. 6 definitely is divisible by 6, but neither of the factors is divisible by, neither 2 nor 3 is divisible by 6, and powering them up is not going to help. All right, so these are the three types of things that we need: general ideals, prime ideals, and primary ideals in replacement for arbitrary integers, prime integers, and prime powers. And now what we need is a connection between primary and prime. Like we had in the integers, each prime power belongs to a prime. So it is the power of some prime number. We have something very, very similar in a general setting if we look at what is called the radical of an ideal. So if you take something that has this primary property, what you can look is at the radical. We write it already as this root symbol because it is actually the set of all possible roots of stuff in Q. So everything is in there, which to some power already lives in Q. So all the roots of all the degrees. And what happens here, if you compare the definitions of prime and primary, well, the only difference is this little k up here. I mean, this is a strong difference and it makes a difference in the properties. But what now happens if we collect all the elements whose roots live already in Q? Well, then we cover this case. And what that means is that whenever I look at the radical of a primary ideal, what I actually get is a prime ideal. So primary ideals and prime ideals behave like prime powers and primes. Every primary ideal has a prime which is connected to it by extracting roots, like for the prime powers, the base. So these are the three things that we need, and these are the things we would like to decompose stuff into. Yes, maybe that should be mentioned. We also call that primary ideal then P primary in order to clarify what is the prime belonging to it. For example, while this is not a surprise, if you look at the radical of the ideal generated by 8, well, it's the ideal generated by 2. 2 is the prime that belongs to 8. For the ideal that we have seen generated by x squared, well, the prime that belongs to it is x. We can do this even more complicated. You might not know why, but the ideal you see here happens to be primary. It has 3 generators. There is an easy checking mechanism, which I will tell you in a couple of moments. And what you need to do is you collect all the variables that you see and just put them next to each other. And then you get the associated prime to that ideal. What we do not have the other way around. So whenever you have an ideal that is a radical of something, and it happens to be prime, like the prime numbers, then you cannot do the backwards implication. The ideal you started with may not have been a primary ideal. So this is the difference to prime powers in the integers. Whenever you have the power of a prime number, well, then it's the power of a prime number. There's nothing to discuss about it. But in this more general setting, if the radical is a prime, then this does not mean that the original primary property was satisfied. And just for the record, I put here an example, which is now not easy to verify because I did not tell you how to verify. I just would like to state it here, maybe for later purposes, that you can see an example where you have a non-primary ideal whose radical is actually prime. And just as a hint, because we will see it in a moment, I told you to find the radical, you just search for all the variables that occur, but actually that's not what you do. You search for all the variables that occur as a single power. So the radical of this ideal is simply generated by x. And this is also the reason why it's not primary, because here you see a y, but y does not occur as a power. We will come to that, back to that later, because yeah, I needed the example beforehand. Sorry for the order. But what we do know is, well, maybe not any prime does the trick, but we know that if it's maximal, then we can do the backwards conclusion. If the radical happens to be what is called a maximal ideal, then we dealt with a primary ideal to begin with. What does maximal mean? Well, maximal means with respect to inclusion in rings, you get chains of prime ideals, and at least in commutative rings, there's always a maximal one, if you believe in the axiom of choice. So might not be the case for all of you, but I mean, we algebraists, we kind of have to live with that. So what does that mean for us? In the integers, everything is as usual. We take a prime number, we can power it up, we get a primary ideal. I mean, you have to look at the ideal. You can do the same thing with maximal ideals. You can power them up, because if you now extract the radical here, what you get is M. And it's again primary due to the blue implication here. This is actually the same thing. Prime numbers generate maximal ideals in the integers because there are no real chains. There is only prime numbers and 0. But we do know that the red implication that I already crossed out is not true. This is even harder to verify, but again, just stated here for the record, this would be an example of a prime ideal. If you look at the second power, it's not primary anymore. I actually had to check that with the computer because by hand, it's really not fun. But what else do we have? Well, we could happen to look at monomial ideals. Monomial ideals are ideals where all the generators that you see are actually monomials and not general polynomials. So what you see here, you see a minus, or it could also be a plus. You see sums of monomials, and they make life very hard in this context. But if all the generating elements are actually only monomials, then we can, well, it's still very hard to decompose, but at least there are many checking mechanisms which allow us to speed up the process in some cases. And in particular, if we take one of those, well, then we can also power it up and it's primary. So they also behave very, very like the prime powers in the integers in this particular sense, of course. All right, finally, I'm there. I can now tell you how to recognize that the monomial ideal is primary. So again, all these M's are just monomials, no sums, no subtractions, nothing. And then if we look at these monomials, we can see with eyes, no computers, no computations necessary, whether it's primary. And how do we do that? Well, we look at each monomial and we check if every variable that occurs as divisor of one of them is also there alone with a power. So for example, you have the generator xy, then you need a power of x and you need a power of y to be primary. And if it's not there, it's not primary. So you do not need to understand the whole ideal. You only need to know the list of generators. And you can already decide by looking at it whether it's primary or not. So if a power of each variable that divides one of the MIs already occurs as a generator itself. This is how we can decide it in monomial ideals. So now let me hop back to this example. Here now with this criterion, you can see that this is not primary because there's no power of y among the generators. But this cannot be primary by the criterion. However, the radical, everything that is in there is divisible by x, so x generates the whole radical. All right, I need to check the watch. It's already a little bit late. Let me just sum up a bit. So what have we seen in this definition section? We have looked at what are ideals, what are prime ideals, what are primary ideals. We have seen what radicals are. We touched monomial ideals a little bit, and we have just seen how to recognize whether monomial ideals are primary. So why am I telling you all of this? I'm telling you all of this because there is a thing like the integer factorization in this general setting, and it's called primary decomposition. I stated as a theorem, at least one theorem. It's the Lascanute Theorem, and it's well known since 1904 and 1921. It depends on in what generality you want to have it. And what we have here is we are living inside of a Noetherian ring named after Amy Noether. What that just means there is some finiteness condition. If you remember the chains of primes that I was suggesting in a Noetherian ring, well, this cannot go on forever. It has to stop. So they cannot be infinitely long. This is kind of a restriction, but for the rings that we have named before, the integers or polynomial rings, infinitely many variables, everything is good. We're in a setting that it works. And what the theorem states is that we can do the same thing as we can do for integers. We can decompose the ideal into primary components. Well, there is not a product anymore. It's now an intersection. And it's not as nice as the integer decomposition because, well, it's in particular not very unique. So what you can do is you can write it as an intersection. You know that you can do it in a way that all of the intersections are primary. You can do it in a way so that you have no redundancies, so that whenever you take one away, you do not get the ideal anymore, but something bigger. But still, it's not going to be unique in general. But, well, let me remind you of the examples before I tell you but. Here, you have this decomposition like we have written it in the product as decomposition of ideals. So this is exactly the primary decomposition as it exists. For the integers, well, it happens to be unique. And as we have already established, the radicals, well, here, except for the first one, they are already their own radicals because they're already prime. But the associated primes, where is the associated primes, what we call them, they are the prime numbers, the base of these powers that occur. And that's what the Lascanute theorem says works in general. Even though the decomposition is non-unique, the associated primes, they are always uniquely determined. No matter with which decomposition you start, you will always get the same set of associated primes. And they are the radicals of these occurring primary ideals. So in this very general setting, it makes more sense to investigate what are these associated primes as the building blocks of the ideal, even though we lose information, but they are at least intrinsic to the ideal and do not depend on the decomposition. So in my research with Irina Swanson, what we want to do is we want to understand associated primes of monomial ideals. And in particular, we would like to know how many of them are there. Let me remind you of the examples. So here again, the decomposition of the shape was nothing else than a primary decomposition, like the decomposition in the integers, but now in ideal language. And for this graph theoretic example, where we could decompose edges into minimal covers and minimal covers into edges, this is also, from an algebraic point of view, exactly the same thing. All three examples happen to have a unique decomposition, but this is because they have a very strong interpretation. So the interpretation from the geometric or the graph theoretic background, they give these ideals very special properties. And that also makes the decomposition unique. We cannot expect that from a general ideal. All right, shortly sum up. We're speeding up the talk. We're almost at the research part. So what have we learned now? We can always do this decomposition. It's unfortunately non-unique, but the prime building blocks, they are unique and they are called associated prime ideals. Also, if you may not remember, this is the first half of the title of this talk. So after only 40 minutes, you understand the first half of it. From now on, it's going to be a little bit faster, but these are the important parts. Let's now look at ideal powers. This is also mentioned in the title somewhere. Ideal powers occur in many contexts. Well, from the algebraic perspective, are very important. To name 3 examples, we can define the topologies with ideals by defining, so if you look up here, we power up ideals, and what we get are neighborhoods of the 0 element, and then we can uniformly shift them around to be neighborhoods of all the other elements. And well, depending on the ideal, we get topologies with certain properties. The more we know about the ideal, the more we know about the topology. And with respect to these topologies, we can also look at completions, complete rings with respect to the topology. So understanding the ideal in terms of its building blocks will give information about the topological properties and the completions in a very, very generic way of saying. It really depends on the situation itself, what you get from it. Something else that comes from algebraic geometry, if you are familiar with algebraic geometry a little bit, then you might remember that in order to understand a geometric shape, what you do is you look at the ring of functions on that shape. So you mod out the defining ideal. And then you get functions on the shape, and you investigate the shape by looking at the functions. What happens is you lose information about the derivatives of the function. And in order to regain those informations, instead of modding out the ideal, you mod out powers of ideals. And again, while the associated primes, they may change with the power. Powering up ideals does not maintain primary decomposition, so they may mess them up. So we would like to be able to understand associated primes powers also from this point of view. And the last example that I bring here today, but definitely not the last that is out there, is also in combinatorial commutative algebra. If you power up edge ideals, or sorry, cover ideals, the ones with minimal covers in them, then you get information about colorings of subgraphs by looking at the associated primes, in particular when they change. So if from one part to the next, something changes in the associated primes, you can make deductions about colorings of the corresponding subgraphs and vice versa. But this is, very complicated to summarize here. So what does my research with Irina's Onsen do? I will keep it short. We take an arbitrary ideal of an Euclidean ring, and while we cheat a little, we take monomial ideals because they're easier to handle, and we're still at the beginning. And then for each possible power n, we have two things. We look at the set of the associated prime ideals of the nth power of the ideal. Well, we may or may not be able to compute them, and we look at their number. And while we are hoping that it's easier to actually compute their number, because it's definitely very hard to compute them, all of them, for an arbitrary ideal. So what we're trying to do is we try to determine what types of sequences can occur as numbers of associated primes. And these sequences, they are called realizable sequences, realizable by the ideal I. And now the question is, what types of sequences can occur? Now, if you take an integer and you decompose it into CD associated primes, if you power the integer up, the associated primes are not going to change. They will always be the same prime numbers. They occur with higher and higher power, but we have already established that we ignore that. So this is just a constant sequence. So what can happen for more general ideal? They are not constant. Do they have to be monotonic? Do they have to have certain behavior? What do they have? And so this is more or less where I will, this is going to be my last slide because I'm already speaking for a very long time. What do we know about them? Well, maybe at the end, I will also ask some questions, which I still have. So we started by investigating what is known. Many, many things are already known. First of all, what we know is that they always eventually stabilize. There is a theorem by Brodmann that has been proven in 1979, who has shown that not only does the sequence stabilize, the set of associated primes stabilizes at some point. So we have to get up, who knows how high, but then at some point they will stop. So there is a point where we can stop computations in theory because they would be too hard anyway. So we know realizable sequences stabilize at some point. Well, then there are a bunch of classes known for which the sequences are non-decreasing. So Actually, the bunch of classes is known for which not only the sequences are non-decreasing, but also the sets of associated primes can only grow bigger. I mean, they could stay the same or grow bigger, but we cannot lose primes that were once associated. To name you a bunch of those classes, well, there's one well-known example by Ratliff coming from the geometric investigation. If you have an ideal whose power have a very special property that they are integrally closed. And by integrally closed, we simply mean, well, I wrote it there next to it for the ones who would like to know the details. That means that these ideal powers have to contain solutions to monic polynomials, certain monic polynomials where these coefficients come from the right power of the ideal. If we have this very strong property, and this is not some arbitrary property, so there are applications in geometry where ideals actually have this property, so it made sense to ask the question. And there we know once prime ideals are associated, they stay associated for the remaining powers, all infinite ones. Another class is what we have seen in the example sections, are cover ideals. So we take all the monomials that correspond to minimal vertex covers. And if the graph happens to be perfect, that has something to do with colorings. So it's again a very strong property. Then it's also known that the powers of the ideals do not lose associated primes. This is not a surprise if you remember, I just previously had said that cover ideals and associated primes of their powers have something to do with coloring. So if you know information about the colorings, you also know something about the associated primes. And the third example in this special section on non-decreasing sequences, definitely not the last example, are edge ideals. So for simple undirected graphs, edge ideals also have these very, very nice properties, which is, from my point of view, very interesting. Here, edge ideals come from simple undirected graphs, arbitrary. For cover ideals, we need the perfectness. But we have seen in the example at the very beginning that there is a dual notion in between, but it does not seem to translate between the two factors. So what else is here to observe? All these two examples, edge ideals and cover ideals, are square free, meaning in the monomials, there are only single variables, no squares. So people started asking around 2012, well, maybe that is always the case. As long as we have square-free monomial ideals, let's shove away all the interpretation and meanings like algebraists love to do that. Let's see whether we can do that. Well, it turns out the answer is no. In 2014, Kaiser, Stillig, and Strekowski were able to show that there are square-free monomial ideals whose associated sequences are not only non-decreasing, they're not even monotonic. And the nice thing is, well, they did this using an old example graph by Galai, and they showed it actually with interpretation and meaning. So it was not possible to throw everything away. And just to show you one of the examples that they have found, this is one of the sequences. It stabilizes here at 45, and the non-monotonicity is just this tiny, tiny fluctuation. So it's almost monotonic, but it's not. All right, so we have non-monotonic sequences. We know that. What else do we know? Well, then people started wondering, what else can we do? And then my Irene Swanson, the person I work with, worked together with the student on, well, what else is possible? And they were able to realize even every non-increasing sequence. So not only do they not all go up or are non-monotonic, we can also do all non-increasing sequences by monomial ideals. Well, of course, they have to be non-negative numbers. They count something. So there are cardinalities. Non-increasing sequences stabilize automatically, so no one needs to worry about that. So these are all realizable. So no, sorry, the question does not appear on this slide, and I would like also to come to an end. So what we are wondering is what types of fluctuations are possible. We have a special class of ideals, which we name after their creators, Bandari, Hebe, and Herzog, where we were able to compute all the associated primes of all powers, describe them in a combinatorial way, and see and determine the formula for the sequences. But the fluctuations are teensy tiny, like the one here. Where is it? Like the one here. So what we can do is go +1, -1, +1, -1. We can determine the length. How long should there be a +1, -1, +1, -1, +1, -1, and then at some point it just stabilizes with a little intermediate section. But these are just like teensy tiny. And they switch every second one. So we are working on constructing ideals which show, well, interesting behavior of all kinds, whatever that may be. And we're still at the very beginning, so there's plenty of open questions there. And this is also where I think is now a good stopping point, 7 minutes over time. Thank you very much for your patience.